Okay. So you need this one here, guys. It says Unit 3B, Principles of Thermodynamics. Okay, or Principles of, energy conversion. It's in your notes package. Okay, should be in your notes package. No, it should be in the notes package you printed off for yourselves. If you don't have it, you need to get your phone out and follow along, or your tablet out and follow along from lesson 2. Okay. Oh, okay. You don't have? Okay. Well, yeah, you don't have this one with Rube Goldberg, this cartoon, right? But it goes.
It goes to scalars and vectors, right?
This here? Okay, hold on. All right, so what we've got then, okay, laws of thermodynamics. Now, let's look at the word thermodynamics. What's thermo usually mean? Okay, temperature, yeah. What else? What else could thermo mean that maybe has like temperature? Heat, yeah, okay? Heat, energy, all right? Thermo means heat and energy, all right? And dynamic means to do what? Move, change, yeah. Dynamic is changing, all right? If something is dynamic, it's always different, all right? If something is static, it's always the same, yes, okay? So thermodynamics is changes in energy or flow of energy or movement of energy, okay, from place to place. So that's what thermodynamics means to us. All right, so all machines in daily life are governed by essentially these 3 laws of thermodynamics. We mostly deal with 2 laws, okay, but there's kind of it's not a 3rd law, it's actually called the 0th law, because it's like a prequel. Okay, the first 2 were discovered and then they found one that should have gone before. Yeah, okay, kind of like Star Wars. Right, okay, so the first thing we need to look at here, though, are systems, because we have to have some terminology or some background if we're going to deal with thermodynamics. So a system is any series of interconnected parts. All right. So any machine essentially that we would use, all right, would be a system. Okay. If we're talking about, let's say, your hair dryer, right? Well, your hair dryer is a system because it's got a heating element, it has a fan, it has resistors, a power supply. All of those things work together to produce the end result, blowing hot air on your hair. Okay, so it's a system. It all works together. Right? If I have 2 people climbing a mountain and they're attached to each other by a rope over a pulley, okay, the 2 people, the pulley and the rope, are a system because energy can be transferred through that system to each other. Right? Because if one person falls, the other person will move up. Well, as long as the heavy person falls. Okay? If it's the heavy person that falls, they will move down. The lighter person will move up. Okay? Now, if the lighter person falls, they will probably still pull the heavy person off. Okay? And then they will both, well, the light person will stop falling and start moving up, and the heavy person will start falling. Okay? Hopefully someone grabs on, okay, at some point. Everybody with me there? Okay, so interconnected parts are a system. Okay, so a system's a set of interconnected parts. So that's probably something worth highlighting there. Whoop. Oh, I can't highlight on that because it's a picture. Okay, forget it. So we got this system here is a set of interconnected parts. So please make sure you highlight that somewhere. Okay, so in studies of work and energy transfers, the system is the object or objects involved in transfers. All right, so if we got the 2 people falling, all right, the energy is being transferred from one to the other. One person is going to be gaining potential energy because they're going to be going up, and the other person is going to be gaining kinetic energy because they're going to be falling down and going faster, okay, as they fall. All right, there's 3 kinds of systems, and they're classified based on how they deal with energy. An open system, and most things are open systems, is one that exchanges both matter, so actual material, and energy with its surroundings. Right? The surroundings are everything that's not directly connected to the system, but is around it. Okay? Can energy flow from the system to the surroundings? Yes, if it's an open system or a closed system, yes it can. All right? So, in an open system, okay, the Earth is an open system. The universe is its surroundings. Energy does go outwards from the Earth, okay, into the surrounding area, okay, things like that. You are an open system, right, which is why the police can follow you with the infrared camera, right? Have you ever seen, like, on cops when the helicopters, got the infrared camera and the guy's hiding under a tree? but he stands out like a sore thumb because he's like bright white in the infrared because he's hot, whereas everything else around is cold. All right, you're an open system. You're always exchanging matter and energy with your surroundings. You breathe in and out. You're exchanging matter, carbon dioxide, oxygen, water vapor. Okay, and you're always releasing energy to the surroundings. Okay, so you would be an open system. Okay, your oven in your house, okay, would be an open system, right? Especially when you open the door. Okay, it's an open system. The heat from inside comes out. Right? A closed system can't exchange matter. It's sealed off. Okay, so a closed system cannot exchange matter. Okay, but it still exchanges energy. So a Ziploc bag is a perfect example of a closed system. All right, when you seal it up, nothing gets in or out. But energy can, all right? So if you made chili or something, you put it in a Ziploc bag and you throw it in the freezer, it's going to freeze, but the chili won't get all over the freezer. Okay? It's a closed system. The chili stays in there, okay? But obviously the energy is lost to the freezer and eventually it freezes. Everyone with me on that? Okay. An isolated system. It's very difficult to build a perfectly isolated system. There's always some loss of energy to the surroundings, even in a perfectly isolated system. Okay? Now, what I mean by that is this. If you consider like the International Space Station, it's got to be pretty close to an isolated system. We can't have any matter obviously being exchanged. It has to be closed for sure, because if there's any matter being exchanged, they'll have explosive decompression. Okay? But it also needs to be pretty well insulated against a lot of things. We don't want cosmic rays from the sun, which we're protected from by our atmosphere, to be hitting the astronauts inside. All right, so it's insulated against those, or isolated from those with reflective coatings on the outside that reflect those forms of radiation away. Okay, it has obviously a lot of insulation for heat. Okay, we want to be able to keep a lot of the heat in, and in some cases, keep the heat out. It depends on what side of the Earth it's on. Right? When you're out in space, the temperature between the in the sun side of the Earth and the in the dark side of the Earth is several hundred degrees. Right? Like on the moon, if you're on the sunny side, the light side of the moon, it can be plus 200 and something. Okay? On the dark side of the moon, minus 200 and something. All right? There's no atmosphere to retain the heat like it is here. I mean, it gets colder at night, obviously, on Earth, but not so radically so. The atmosphere traps a lot of energy for us. So the International Space Station is close to an isolated system, but it's not perfect. Some stuff still gets in. Some of those stray cosmic rays come in and hit the astronauts. Okay, some of the heat gets out. All right, things like that. It's actually not even a perfectly closed system because the space toilet does jettison some stuff. Okay, you guys ever seen how the space toilet works? Yeah, it's yeah, interesting. Hey, peeing and pooping in zero gravity is an entirely different animal. Okay, you think about it. You rely on gravity an awful lot in the bathroom. Okay, no zero gravity, stuff gets everywhere. Okay, and you can't have that happening because if you inhale any of that, you can get really, really sick. Okay, so it'd be very bad. So there's a little bit of a they actually vent to the outside a little bit to create a suction, so that stuff gets pulled away from you as it comes out. Yeah? They often describe it as it's a little windy in the bathroom on the International Space Station. Okay. All right, so the International Space Station is like close to an isolated system when it's all sealed off because it sort of has to be, but it's never perfect. There's no way to perfectly isolate something from everything else. All right, first law of thermodynamics is the law of conservation of energy. All right, now we talked about the law of conservation of matter back in the first unit. The law of conservation of energy is pretty much the same thing, except substitute energy for mass. All right, energy cannot be created and it cannot be destroyed. Right? But it seems like it can. All right? Because we see energy being lost. Okay, and we say, well, it's lost, it's destroyed, it's gone. But it isn't. It's just being transferred away or turned into other kinds of energy that are no longer useful. Okay, and that's because most of the machines we use on a daily basis are highly inefficient. Okay, and so we see that we had all this energy, but it's gone. Okay, well, it isn't gone. It went into the surroundings. Okay, it turned into heat and it heated up the area around you. All right, you take your car for example. Your car runs at roughly about 16% efficiency. The rest of your car's energy and the fuel is turned into what? Heat. Okay? There's so much heat generated by your car through the expansion of the gases, which is what you want, okay, in the burning of fuel, but also in the friction between all the moving parts, that your car has to use 30% of the energy within it to keep itself from melting down. All right? 30% of the energy in your fuel is used to run the cooling system that keeps your car from seizing. Okay? Circulates the antifreeze, the coolant through your car. Okay? That uses 30% of your fuel. Weird, huh? Okay? That's why hybrid cars are a little more efficient. Yeah, cool. Electric motors are very efficient. Very efficient. The issue with using an electric car isn't so much about the job it does, which is transporting you from place to place. It's people have been misled a little bit as to if you drive an electric car, you don't pollute the earth, which isn't true. Because where does your electricity come from? Yeah, what do we use in Alberta to make power? Coal. Okay, like coal is the dirtiest fuel there is. Okay, and like 85% of all electricity in Alberta is generated using coal. So if you have an electric car, you're not doing anybody any favors. You're just making a heavier draw on the coal plant that's making your electricity and is putting carbon dioxide into the atmosphere for you. So you can distance yourself one step from the pollution, but you're still doing it. Okay, so people have kind of been misled in that regard. They're like, "Oh yeah, if you drive an electric car, if you drive a Volt, you're doing wonders for the environment." Well, not really, unless you're connected to a wind turbine and that's the only thing you're using to charge your car. Okay, then maybe. All right. Well, even solar power. There's a lot of really harmful chemicals in solar panels, and when they go, you chuck them, right? Like, so there's always a drawback. People are like, well, what about nuclear power? That doesn't make any. Okay, yeah. You ever seen the waste, the green goo that comes out of there? Okay, it's radioactive for tens of thousands, if not hundreds of thousands of years. They just bury it in the ground and you forget about it. Okay, well, that's why there's only a few places in the world where they actually do it. Certain types of bedrock lean themselves better to not leaking. So when they take the radioactive material, they put it in first a steel container, and then they encase the steel container in concrete, and then they bury it in these special vaults, okay, that are in a certain type of rock that doesn't leach. Okay, and then they fill those caves or areas up with concrete. Yeah, so it's sealed in there for all time, essentially. Okay, so it should be, we hope, safe. Okay, for hundreds of thousands of years. Yeah. Okay. So there's always something to think about, right? You kind of always have to look past things. Is a hybrid car a good thing? Sure it is. Okay. Is it use less fuel? Sure it does. Does that mean less pollution? Sure it does. Okay. But it's a matter of, did you buy it for that? Did you buy it for the right reasons? Okay, it costs roughly $33 million to launch lightweight spacecraft into space. So launching huge amounts of mass into space is not a really economically viable way to get rid of it. Yeah. There's all kinds of ideas, okay? Yeah. Maybe. Okay, so energy can't be created, it can't be destroyed, but it can be turned into other forms of energy that no longer do useful work. And that's why we sometimes think that, well, the energy is gone, it was destroyed, it was lost. Well, it might be lost from the system. It might go to the surroundings, but it's still around. Okay, it's still there, it's not being destroyed. Okay, in the same regard, you can't create energy, right? There's no machine that will make energy. All machines convert energy from one form to another. All right, so we take chemical energy in gasoline, we turn it into mechanical energy in the car. All right, and that drives the car forward. It's a conversion. We didn't create it. It was already there in the fuel. Everybody follow? Okay, photosynthesis is transferring, changing energy from sunlight into chemical energy. Right, we're taking all of those conversions from time to time. All right. So the energy of a system can decrease in two ways. Okay, if I have a system and its energy decreases, I've either lost energy to the surroundings or my system has done work on something else. Okay? Work is a transfer or a change of energy. Okay? So whenever you do work on something, you lose energy. That's why you get tired when you're working. All right? If your job is to, I don't know, dig holes, okay? Do you get tired? Yeah, because you're doing work. You're lifting dirt and throwing it onto a pile. All right? That's taking energy. You're doing work. You're changing the energy of the dirt and moving it from place to place, and eventually you get tired and hungry, and you'll have to, eat something and take a little break, and then you'll have more energy and you can do more work. So a system can lose energy either just by losing it to the surroundings. Okay, we call that heat. Heat is a transfer of thermal energy. Okay, heat itself isn't a form of energy. Heat is a transfer of thermal energy. Okay, and work is a transfer of mechanical energy. So when you do work, you actually move something, okay, or change its shape in some way. Okay, does that make sense to everybody? Yeah. Okay. So first law of thermodynamics is, like we said, just a restatement of the law of conservation of energy. Okay. All right. Okay, so most machines, like we said, involve many moving parts that are in contact with one another. Anytime you have two parts sliding past each other, there is friction, and friction generates heat, and then the heat is lost to the surroundings, and it makes it seem like the system has lost energy. It hasn't. It's done work against friction, and that's resulted in heat being lost. All right? So are there ways to make things more efficient then? Yes. Yes. The energy that is crushing the object comes from the gravitational potential energy of the water above. Right? The weight. The weight of the water above creates pressure, and that's because gravity's pulling it. Right? You disturb the water by dropping something in. Okay? That disturbance eventually gets alleviated when the thing is crushed flat. Yeah? So changing the shape of something is work because it requires mechanical energy. All right. Now, how many people have heard of a perpetual motion machine? Heard the term before. Okay. A perpetual motion machine is supposedly a machine that can run forever and not require you to put any energy in it. What's the problem with that? Right. Why not? Why can't it exist? Okay. I always have to put stuff in. Why do I always have to put stuff in? If a machine is running, once I get it running, why can't it just keep running? Why does it run out? That's what I'm trying to get to here. Why do machines eventually run out of energy? Even if they're not really doing any work, they eventually run out of energy. Okay, but if it's not doing any work, it's just running, why does it eventually stop? Right. Okay, its initial energy is being transferred away. Okay, it's doing work against what we call non-conserved forces. The most common non-conserved force is friction. All right, there is no way to eliminate friction from a system. There's always going to be some. Okay, and any time one form of energy is converted to another, energy is lost. Okay, energy is lost to the surroundings. When we convert chemical energy into mechanical energy in our car, we lose almost 60% of it as heat, right? Because we're setting fire to the fuel, okay? Most of that heat is not doing any work. What's doing work is the expansion of the gases inside your car's combustion chamber that push the piston down, all right? But the heat, it doesn't do anything, all right? It just gets transferred away, all right? If you've got, even a puck sliding along the ice, ice is, pretty slippery. It doesn't have very much friction, but a puck eventually stops. Right? It eventually slides to a stop. Okay? In curling, same idea. Okay? Or as I like to call it, paint drying. Okay? When a rock slides down the ice, it eventually comes to a stop, unless you throw it like me. I like to throw takeouts, even when there's nothing in the way. I like to throw takeouts. Okay? So the rock will eventually slow to a stop because there is some friction. It's slowing to a stop, and you can hear it. You can hear the friction as a curling rock slides along the ice. Okay? You hear the rock grinding against the ice. Okay? Is there heat produced there? Yes, there is. In fact, we use that to our advantage if you've ever watched paint drying, I mean curling. You have the two people with the brooms, right? Okay, and they're sweeping in front of the. They're not trying to actually clean the ice. The ice isn't dirty, okay? Which I didn't know for the longest time, but okay. What they're doing is they're melting the little beads of ice that are on the surface, right? If you've ever seen curling ice get prepared, they take a hose and they just spray droplets of water that land on there and freeze into these little beads that are on the surface. When you rub those with your broom, okay, there's friction there and it melts that ice, and the curling rock slides more easily across wet ice than it does across dry. All right, and so when they do that, they can steer the rock a little bit, okay, depending on where they sweep, and they can make it go further because they reduce the amount of energy being lost to friction while it slides along that narrow layer of water. The skates don't so much melt the ice as they cut into it and allow you to anchor yourself in a groove, right? That's why they have to be sharp. Yeah. Okay. So like if you've ever seen like a good skater, if they are on a freshly flooded sheet of ice, they leave big cuts in the ice when they're pushing, right? And that's because they're actually cutting into the ice and getting themselves a good anchoring point to push off of. Yeah. Okay. So yeah, there's always these energy losses. Okay, even in systems that seem like they shouldn't have an energy loss. Anytime you convert one form of energy to another, you lose some. Okay, and usually you lose it as heat, sound, and sometimes as light. Right? All of those can be kind of wasted forms of energy. Right? If you look at light bulbs, they're another example. Okay, what's their initial energy for a light bulb? Electrical energy, okay? The energy of moving charges, all right, is what powers a light bulb. Now, if we're talking not so much about a fluorescent light bulb, but let's say the old-fashioned incandescent ones, okay, with the filament inside. Okay, that electricity gets turned into what? Heat and light. Incandescent means to get so hot that you glow, all right? So incandescent light bulbs are not very efficient. They're very, very hot. They've been on for like 10 seconds. You can't even touch them. Right? So they get very, very hot, and as a result of being very hot, they glow and give off light. Light is like 10% of the energy that a light bulb produces. Or yeah, it's less, depends on what kind, right? Okay, and you've got now, obviously, replacements for those. Incandescent bulbs being replaced by compact fluorescent and LED because those produce very little heat and mostly light, and so as a result use way less energy. They waste less energy. Okay, does that make sense? We convert one form to another, and when we do that, other forms of energy are produced, like heat. All right, so perfect machines obviously can't exist. These are some of the ideas people had for perpetual motion machines, okay? Things that would be able to run forever. Now, here's the problem with a perpetual motion machine. Even if you can build one, which you can't, but even if you could, it would never do anything useful. It would never do any work, because work is a transfer of, okay, if you're not putting energy into it and it does work, it will stop, because it would have transferred away some of its energy. So even if you could build a perpetual motion machine, it wouldn't do anything other than just go. You couldn't use it to do anything, because it can't. If you're not putting energy in, you can't get any energy out. You can't create energy, you can't destroy it. So a perpetual motion machine would simply be a scientific curiosity, even if you could just build one, but it would never do anything useful. No, because something can't fall forever. Right? And you have to get something up to that height. You have to put energy in to get it up there, right? So again, it's not, I mean, these are kind of, this one is supposedly running on that idea. Okay, this first one here where, you know, it's got these curved blades of this kind of fan-like thing. So these fall to the bottom and push on the outside, and as they're coming up on this side, they roll to the inside where they exert less force, okay, and it supposedly continues to spin. But what's the problem right here? There's friction. Okay? Anytime there's two surfaces in contact with each other, there's friction, and that thing eventually slows to a stop. It is always falling, yes, but it never gets any closer, because it's moving fast enough that it the distance it falls is equal to the distance the Earth curves away from it because the Earth is round. Okay? It's not a perpetual motion machine. It's been given enough kinetic energy that it can stay there. Right? Okay, this one here I thought had some merit, okay, as an idea for a perpetual motion machine. Okay, it's got these metal balls, and they get attracted to the magnet. The magnet draws them up the hill, right? And then they fall through this hole and slide back down, and then they go through here. Here's the weakest link. They have to do what with this little door? Open it. Does that work? Yep, and eventually they'll slow down and lose energy, and this thing will stop. Okay, even with that magnet there, this isn't always going to keep going. Yeah, there's friction on the board. There's friction. I mean, the friction on the board up isn't an issue. The magnet is overcoming that. Okay, it's the issue of here, the friction on the way down. It's losing some of its energy, and maybe it doesn't have enough when it gets to the bottom to open the door. Right? So, and you'd have to have it perfectly timed, because otherwise you might have one going this way when this ball is coming here. Right? You could never probably have more than one ball in this system at a time. Well, the hole is before the magnet, right? So they would fall through the hole before they get to the magnet. Well, except that when they get to this hole, they can't jump the hole. Gravity will be a stronger force than the magnet. I mean, you'd have to set it up that way, right? Yeah, if this was a really strong magnet, they might just go straight across and jump the hole. So you'd have to make the hole big enough, right, that they would fall through it. Okay, but again, there's still going to be energy lost to the surroundings, and that's going to result in it stopping. Okay, so that's the second law of thermodynamics. Energy always flows just like diffusion flows, from high to low. Okay, it flows from high energy to low energy. All right. We always say, when someone opens the door, to the house when it's really cold outside, close the door. You're letting all the heat. You're letting all the cold air in. No, you're letting the heat out. Okay. Cold doesn't flow from cold to hot. Hot flows from hot to cold. All right. If you're treating someone with hypothermia in the wilderness, what are you supposed to do? Nobody knows? Okay, well, I'm going to teach you a life-saving lesson then. Okay? You're supposed to both strip down and get in your sleeping bag together. Keep your mind out of the gutter, though. Okay? You're trying to save this person's life. Okay? The reason that works is because heat flows from you, the hot person, to them, the cold person. Now, eventually, you're going to feel colder. You're giving them energy. You're going to get colder. I mean, it's like when someone comes in, they've been outside and they sneak up behind you and put their cold hand on your neck, right? It feels cold. Why do you feel cold? Because you're losing energy to their cold hand. Okay? Heat always flows from hot to cold, right? That's why when you leave, like my coffee cup, and my coffee's already cold because heat flows from it to the surroundings, right? No matter how well insulated or not that Tim Hortons cup is. Because they actually, it interferes with their ability to regulate their temperature properly. Yeah, being severely burned, yeah. Plus, you don't want to have oxygen getting to the wound because that can increase the rate at which the tissue degrades, and that's painful. So, yeah, when you have a burn, the best thing to do is cover it up right away and eliminate the oxygen from the wound because it'll make it feel better. Yes, there's special types of fabric that you're supposed to use for a burn. Yeah. Okay. So big thing here with the second law of thermodynamics: heat always flows from hot to cold. Okay, and not just heat. I mean, it's mechanical energy as well. All right. If something's moving really fast, okay, and a low energy object is coming towards it, okay, yeah, okay, when they hit each other, which one transfers energy to which? The fast object or the slow object? Yeah, the fast object transfers energy to the slow object. All right. That's why the fast object slows down and the slow object speeds up. I mean, it's not always speeds up. If it's a head-on, they actually speed up in the other direction, which is slowing down forwards, but you get the idea. Okay? Right? They're transferring energy. The more energetic object always does the work, okay, on the lower energy object. Energy always flows from high energy to low energy. Okay? Does that make sense? Yeah? Okay. All right. Now, the idea of this led people to think they could build something called a heat engine. Okay? And a heat engine would be like a perpetual motion machine, but not truly one. Okay, it would use the fact that energy flows from hot to cold to do work. So they figured if I have a hot area and a cold area, and I put my motor in between, I can use the fact that energy is flowing this direction to do work, because I'll just put whatever I want in the middle. This idea works. The problem is the difference between hot and cold has to be so great, okay, that it doesn't happen without the input of a whole bunch of energy. All right? A jet engine is a heat engine. All right? And in a jet engine, what you have is the combustion area where you burn kerosene, okay, jet fuel, okay, and it's really, really hot. Behind that is a fan. Okay, that's what essentially a jet engine is a series of fan blades. Okay, and behind that is the very cold air, okay, comparatively cold to the combustion area. Everyone follow? The heat naturally flows through here, turning the fan, which produces thrust. All right, that's all a jet engine is a heat engine. Okay, now the idea was that this could be used to power ships on the ocean without any fuel, because the surface of the ocean is hotter than the deep parts of the ocean. So the idea was you would have two pipes that would be attached to your ship. One that would just be, you know, a few centimeters, maybe let's say 50 or 60 centimeters into the water. All right, and you'd have this one pipe that was really, really deep. Okay, went down 100 meters, right, to where the water was much, much colder. And so energy would flow through the engine and down into the cold water. Well, yeah, it would only work in deep water. Theoretically, it would only work in deep water. Here's the problem. Is that hot water already in contact with the cold water? Yeah, why? What's its motivation to go through the motor? Right? Why would you go that way when you're already in contact with the cold water? It's already naturally cycling, okay, in the ocean, so it doesn't work. Right? It's one of those, it's great in theory kind of ideas, but not so great in practice kind of ideas. All right? Okay, so this was the idea here. Okay, this was the ocean-driven heat engine. Right, but again, for this to be effective, there has to be a huge difference between the hot and the cold side of the heat engine. No, because everyone knew it wouldn't work. Okay. Okay, but I mean, essentially, guys, this is how, I mean, all engines essentially are kind of like heat engines. The one in your car, still the same idea. Okay, what moves the pistons up and down is the fact that when you burn gas, it gets really hot. Okay, and hot gases take up more space than cold gases, and when they do that, when they take up more space, they can push the pistons down. All right, and that's what does work in your car, is these hot gases pushing the pistons in your engine downwards. Okay. All right, yeah, so that's all there is to do with that. Okay, now, so heat engines like a jet engine. A heat pump is something entirely different. A heat pump works against the second law of thermodynamics. It forces heat into an already hot area. It's kind of like active transport. Okay, it works the wrong way. If you're going to work the wrong way, you have to use energy to make that work. All right, so an air conditioner and a refrigerator are both heat pumps. And what happens with both of them is you've got something that's capturing energy, okay, taking in heat, and then being moved to another place where it can be expelled. Okay, but it has to be forced outwards. So in both a refrigerator and an air conditioner, what you have, okay, is this. You have a series of interconnected pipes, okay, that are full of coolant. All right, so there's kind of this inlet, okay, that goes to these, okay, and then they all come out this way. Now what they use, okay, is a compressor. That's that big loud thing that you can hear underneath your fridge. Okay, the thing that you guys all know what I'm talking about when the fridge kicks on, that's the compressor, right? What it's doing is exactly as its name would imply. It's compressing the coolant. What happens is, as the coolant goes into your fridge, it takes energy from the food in your fridge. All right? And when it does that, it changes from a liquid to a gas. That takes energy. So it changes state from liquid to gas and then goes back to the compressor. All right? So it's absorbed energy and it's made your fridge colder. When it gets back to the compressor forces it back into a liquid state, and all that energy is released. Okay, we'll talk about the rest of that tomorrow.